All right, well, welcome back. We're going to dive right in. I'm not even sure we're going to get through chapter 10 before the end of the semester. It just keeps going. In case you've been paying attention, the theme has been addition reactions, and we're still not, and elimination reactions. We still haven't really got to elimination, so whatever.
I like chapter 10.
Right. So last time we were talking about conjugate addition reactions. So I'll just copy this over and we'll take a look again. You've maybe heard it described as a 1,4 addition or a Michael addition, especially when you're using carbanion type nucleophiles is when you call it a Michael addition. Let's see, we talked about why it's called a 1,4 addition, and that is because protonation actually happens to be just a little bit faster on the heteroatom. And so what happens after you attack the beta carbon is you get an enolate, which protonates on the oxygen to give you an enol, which then tautomerizes to the more stable keto form. All right, and that is it for the sort of 2-electron nucleophilic addition type of chemistry. And at this point, before we move on to radical addition reactions, your text pauses, and it's sort of out of place, but it's a decent enough time to do it because the reaction we just described is involved in what your text is going to talk about here. And that is to think about the efficiency of cyclization reactions. Because you could imagine making a macrocycle, making some kind of 5, 6, 7 or so on membered ring using at least some of the reactions that we've talked about, in particular this conjugate addition reaction. So your text pauses and talks about a set of empirical rules for cyclization reactions that most organic chemists are decently well versed in. And so it's important for you to know these because when you go to propose to a particular reaction to your advisor, hey, I want to do this, the first thing they're going to say if you're making a ring is, well, let's see, that's a 5 exo-dig cyclization or a 5 endo-trig cyclization. Is that favored or unfavored? And you'll sort of need to pay attention to that. So these rules were developed by a chemist with the last name Baldwin, so they are called Baldwin's rules. They are mostly empirical, meaning they're just based on data and observations that describe the efficiency of a cyclization reaction. And they're not, as I said, there is some basis in molecular orbital theory and ring geometry, and I'll show you some calculated structures I did to try to illustrate this principle for you guys because it wasn't exactly clear just looking at the structures on paper. But Baldwin's rules break down every ring-forming reaction into 2, or rather 3 basic determinants, 3 basic categories. The first is ring size. Okay, and the second is hybridization of the atom being attacked. The atom that the leaving group is on. And because we can't keep things simple, we make them as complicated as possible. So if the atom being attacked is sp3, we call that a tet cyclization for being tetrahedral. If it's sp2, we call it trig for trigonal planar. And then this is the one where I'm like, okay, whatever. If it's sp, they call it dig. Di something or other, linear, yeah, not sure exactly where it comes from, but that's, if it's dig, that means the atom that gets attacked is sp. And then the third factor is this issue of whether the leaving group on the atom being attacked, this is alternatively, if it's not like a substitution reaction, if it were like attacking a carbonyl group, the leaving group, or the atom that has a minus charge, a plus charge, or a radical in the intermediate. And the question here is it inside the ring, part of the new ring? And I guess I'm going to, instead of saying inside, we'll just say part. Is it part of the new ring? Or outside the new ring? If it's part of the new ring, we're going to call the cyclization endo. If it's outside the new ring, we're going to call the cyclization exo. Okay, so this is easiest to see with some examples. So I will give you an example of a cyclization that works. Okay, here is an alcohol, an alkyne that's conjugated to a ketone. All right, and this is an alpha beta unsaturated carbonyl compound. So in the presence of base, we remove the proton on the alcohol. And then we're going to do a conjugate addition where the alcohol attacks the beta carbon. All right, so we can push arrows like this. And, you know, remember we push arrows to make the enolate. At this stage, let's count the number of atoms in the ring that we just formed. We made a bond between the oxygen and the beta carbon. One, two, three, four, five. Here's the beta carbon. The beta carbon should be doubly bonded to the alpha carbon. And then the alpha carbon should be doubly bonded to the carbonyl carbon. And there's our enolate. Okay. And if that's a little confusing and painful, I'll actually draw out the carbon. That central carbon is, that alpha carbon is sp hybridized there. Okay. With me so far on that reaction? Okay, so let's talk about what kind of cyclization this is. By the way, this reaction is favored. It works just fine. Probably, as with all conjugate additions that we've talked about, you protonate, on the oxygen first. I'm sorry, on the negatively charged oxygen first to get the enol tautomer, and then probably this tautomerizes afterwards to give you the more stable alpha beta unsaturated carbonyl compound. Okay, so for this cyclization, we made a 5-membered ring. Now, the atom that has the negative charge, we could have, in this step, we could have put the negative charge on the alpha carbon. We chose to draw the enolate. Is that alpha carbon part of the ring or outside the ring? It's outside after the, right? It's because we attack the beta carbon and the place the electrons go is outside the ring. Okay, so we call that an exocyclization. So this is a 5-exocyclization. And now we talk about the hybridization of the atom being attacked, which is sp hybridization, right? So we're going to call this a 5-exo-dig cyclization. Dig refers to the hybridization of the atom being attacked. 5 refers to the fact that we made a 5-membered ring. And then exo refers to the fact that the atom that has the negative charge, the alpha carbon, and we haven't drawn the resonance structure where it has the negative charge, but we could have done. In any case, that alpha carbon is not part of the ring. So that is a 5-exo dig cyclization. Yeah?
Wait, can you explain why it's exo again? Why did you name those?
Yeah, the issue of endo versus exo is when you make the ring, you attack an electrophile and the electrons have to go somewhere. Wherever they go, is that inside the ring?
Okay.
If so, that's endo. Is it outside the ring? That's exo.
Where the electrons are going.
Yep.
Okay.
Yep. All right. So Baldwin did a survey of the literature and they looked at a ton of different ring sizes. And in general, and cyclization efficiency as a function of the blue, the pink, and the yellow. Ring size, exo versus endo, and then hybridization of atom being attacked. In terms of ring size, what they observe is what you would expect based on a combination of ring strain and degrees of freedom that you're constraining in the ring being formed. So 5-membered rings are a little bit easier to make than 6-membered rings. You might say, hold on, I thought you said that 5-membered rings were a little more strained than 6-membered rings. That's true, but why would 5 be easier?
Does it have to do with the envelope? Or am I just thinking about it?
Well, you're thinking about ring conformations, and that's right. I mean, the issue of ring conformation is after you make the ring.
Is it just closer?
Yeah, it's closer in distance and also fewer rotatable bonds between atoms 1 and 5 versus atoms 1 and 6. So you've got offsetting issues of ring strain versus degrees of freedom, and empirically it appears that 5-membered ring formation is just faster than 6-membered ring formation, probably because the entropy issue dominates. 6-membered rings faster, but now 3-membered rings are slower than 6-membered rings, right? Why would that be? What's the explanation there?
The ring strain.
Introduced ring strain, right? Yeah, that's over because there's so much ring strain there. That's overcoming the fact that atoms 1 and 3 are actually pretty close to each other. But 3 is faster than 7. It's nuanced, which is faster than 4. You probably wouldn't have predicted this. Maybe somebody could do some calculations and predict it. It's not something to memorize, but it's something that you can consult as you go to do cyclization reactions. And then 8 to 10 is a little bit worse than a 4-membered ring in terms of efficiency. Okay? So again, why is it not consistent? Why are we hopping around all over the place in ring size? These offsetting issues of entropy. Versus ring strain. And the reason we stop writing things down after 8 to 10 is rings that size are essentially not strained anymore. There are some ring strain issues that get introduced in the range of 8 to 10, sort of what we call transannular interactions, groups across the ring actually bumping into each other. Okay. So it turns out that just empirically there's a big table of things, but you don't actually need to memorize all of it. In fact, you need to pay attention to very little of it. The first big observation is that it makes no difference at all how 6 and 7-membered rings are formed. That is endo versus exo. Yay! Both are fine. Tet, dig, trig. That's going to annoy somebody because they're not in order of SP3, SP2, and SP. All are fine. Okay? So 5, 7-membered rings. That's another reason why we like 6-membered rings, is because if you make a 6-membered ring, nobody's going to bug you about whether it follows Baldwin's rules. The second major issue is, or the second thing that simplifies this, is that all exotet cyclizations are fine. What is an exotet cyclization? it's pretty hard to think of anything other than SN2 reaction. So making an SN2 reaction is making a ring via an SN2 reaction is fine for any size ring. So let me give you an example of an SN2 style exo-tet cyclization. Some of you maybe remember using beta dicarbonyl compounds in your introductory OChem class, and you could make the enolate, right? And then you can close the enolate. You've got a leaving group within 3 carbons. Okay. So hybridization of the atom being attacked, that's the one that has the leaving group. That's sp3, right? So that's a tet cyclization. There are 3 atoms in the ring that's being formed. Now, this is the part that can be more difficult to see. What kind of cyclization is this? Exo versus endo.
Exo.
It's exo. Good. How do you know?
The electron are not, the stuff that gets the electron is not part of the ring.
That's exactly right. The thing that gets the electrons is the leaving group, no longer part of the ring or even the same molecule. We still call that exo. So this is an example of a 3 exo tet cyclization. And that works just fine. But in general, any size ring you want to make via an SN2 reaction, they're similarly efficient. So you should not bother memorizing any Baldwin's rules for 6 or 7 membered rings, because it makes no difference whether it's endo versus exo or tet, trig, or dig. You should also not bother learning that all of the exo-tet cyclizations are fine. I mean, you should also not bother memorizing 3 exotet is fine, 4 exotet is fine, 5 exotet is fine, 6 exotet is fine, and 7 exotet is fine, because they're all fine. And as who's the, let's see, it's Dash from the Incredibles movie. And if everyone's special, then no one is, right? If they all work, then why are we even worrying about it, right? Okay. But there are some interesting trends in the range of 3, 4, and 5 membered rings when the carbon that you're attacking is sp2 versus sp3 hybridized, and whether the atom that gets the electrons, the thing that gets the electrons, is inside the ring versus not. So we'll talk about those. And anyway, this comes up enough. For example, anytime anybody's working on the radical, amino radical polymerization stuff, or not polymerization, but ring closing stuff in Steve Castle's lab, if somebody mentions it's a 5 exo trig cyclization or something like that, right? And that's therefore fine. All right. So here are the rules for 3, 4, and 5 membered rings. Again, understand that they're empirical, but I'm going to show you some examples, and you'll get a sense for why maybe the ones that are disfavored don't work out that well. So we're going to have 2 categories, endo versus exo cyclization, and within those 2, we're going to have the dig versus the trig. I'm going to write down SP versus SP2 here just to help us out. And I don't know, we maybe don't need to spend a huge amount of time on this, but it's an interesting issue with geometry, and it is something that you just want to be aware of the things that organic chemists use to flex, and especially when you're giving a talk and somebody in the audience wants to make you look stupid or something like that. This is one of those issues where they can. Well, don't you know Baldwin's rules? Well, yeah, I haven't exactly thought about that yet. Anyway, so this will help you avoid uncomfortable situations. Maybe at the spring research conference, I'll be the jerk in the audience trying to ask this question, right? Okay, so for dig cyclizations, exo-dig cyclizations, they don't work very well for 3 and 4 membered rings. They work great for 5 membered rings. All of the exo-trig cyclizations are fine. For the endo-cyclizations, interestingly, all of the dig cyclizations are fine. None of the trig cyclizations are fine. Okay.
Because the SPG doesn't want to keep the electrons.
Well, let's talk about that. So, and there's, text didn't actually, after bothering to do all of this, they didn't actually bother to give a huge number of examples. So there are a few, and these ones that we did, the ones that they give you, I did actually do calculations on, so I can show you, not of the transition states, but just of the optimized starting material structures, and showing you where the orbitals are. You can get a sense for why things are this way. So why might some be favored versus others? Well, what do you remember from last time when we talked about the Berge-Dunitz angle? Nucleophiles have to approach carbonyls from a certain trajectory, right? It's 105 degrees if you're attacking the alpha carbon. There are similar issues associated with attacking alpha-beta unsaturated carbonyl systems. So the original Berge-Dunitz work was related to a nucleophile being in the presence of a carbonyl group, and that 105 angle is because that's where the pi star is, remember. However, we've seen, it's going to make this really easier, maybe. Yep. Okay, here's an alpha-beta unsaturated aldehyde. The LUMO is on both the alpha-beta carbonyl carbon and carbon and the oxygen of the carbonyl group. But at least as far as the beta carbon is concerned, this looks very much like a pi star. You're going to have Berge-Dunitz angles issues here. There's going to be a preferred angle of approach. Nucleophile has to be able to overlap with that LUMO. So we're going to see that one of the reasons some of these cyclizations are not favored is because it's hard for the nucleophile, given the ring constraint, to get into the right position where it could even attack where the pi star is. So I'll give you an example of a cyclization that's disfavored. All right, this is an alpha-beta unsaturated carbonyl compound. Here's the atom that's going to get attacked. The idea here would be to do a base-promoted cyclization to make the alkoxide, and then to have the alkoxide attack the beta carbon via conjugate addition. But the problem is that the reaction doesn't work. Let me draw the desired product. It would be this lovely 5-membered ring. Okay. This is a 1, 2, 3, 4, 5. So this is a 5. Now endo, because if we had the nucleophile, which is the alkoxide, attack the beta carbon, the atom that gets the negative charge, the alpha carbon, is now part of the ring. Do you see that? The proposed mechanism would be negatively charged alkoxide attacks and does conjugate addition. We could draw either resonance structure. I mean, this is the proposed enolate intermediate. Sorry. Where I'm leaving the negative charge on the alpha carbon just so it's clear where it is, right? By the way, do you notice the Thorpe-Ingold effect? They've got the gem dimethyl group there. They're trying to promote cyclization. Still doesn't work. It's an endo, and the hybridization of the atom that gets attacked is trig. 5-endo trig cyclization, go up to the table, and indeed it doesn't work. Now this really sort of blew my mind because, well, let me just show you the example that does work. I'm going to keep everything the same, only now we're going to do that. Again, the proposed mechanism has the alkoxide attacking the beta carbon of an alpha beta unsaturated carbonyl compound. The thing that gets me here is that it looks like, just because of what an alkyne is, that beta carbon just got farther away. Okay, so that looks like a problem. But this one goes off without a hitch. To give you this product in the presence of base. Again, maybe I'll draw the intermediate after what happened. Moreover, it looks like that negative charge isn't necessarily stabilized by resonance. I mean, if you're sort of following along with what happened, the carbonyl is already conjugated to that double bond, so that's just a carbanion. Apparently not an issue. Or at least apparently, you're able to protonate and move on without a lot of trouble. Okay, this one, we need to classify it. Again, it's a 1, 2, 3, 4, 5-membered ring, and the atom that gets the negative charge is now part of the ring. So we would call this a 5-endo dig cyclization. Sorry. Man, don't you hate it when that... Excuse me, that was the sneeze that wasn't and then was. 5-endo dig, just fine. Okay, yeah.
Hey, why does it not form ethanol? Why does it just make that?
I'm just trying to figure out, I mean, I suppose you could push arrows and do that, but that requires the alpha carbon to be linear. The enolate would look like this. That's what I meant by it's probably not that conjugated, because maybe you can make this, but that's a highly strained sp hybridized carbon. Yeah.
Putting those two double bonds together makes me want to, it makes me uneasy.
Good. It should. It should. That's like.
Yeah, that makes sense.
It's like really trying to. Yeah, and so there are issues here, but apparently they're not insurmountable. So getting a sense for why, and your text sort of leaves it at there. Oh, this one works, this one doesn't. Gee whiz, look at these empirical issues. So what I went and did some calculations, and these should have been easy and ended up being tricky. I used something called natural bond order, which instead of doing the full delocalized molecular orbitals will actually show you individual bonds and anti-bonds, so you can think of things sort of as we have this hybrid MO theory and valence bond approach. So on the left are structures for the 5-endo trig cyclization. Here are the two methyl groups. Here's the oxygen that's going to get deprotonated. Here's the carbonyl. Here's the double bond. Here's the benzene ring. Here's the pi star. Here's your alpha carbon and your beta carbon. And then on the oxygen, this is the p-rich lone pair orbital. You can think of another one that would be going out orthogonal to it, perhaps the sigma out type orbital. But the point I want to make is that if you look at it from the side, at best, there's no way for that lone pair to reach over and access the Bürgi-Dunitz angle with respect to that pi star. At best, it's sort of pointing at the node. So you've got some orbital overlap issues in terms of geometry. Okay? Now the big difference with the alkyne is that the alkyne has two pi stars. One of them is lined up with the plane of the carbonyl group. The other points straight out orthogonal to it, sort of in the plane of the page. So this is our overhead view of the alkyne, carbonyl, alpha carbon, beta carbon. This time I actually did find somehow the sigma out lone pair on the oxygen. I didn't worry about that too much because that oxygen's getting deprotonated anyway, and in that case I don't know which lone pair is, I don't know what kind of orbital p or sigma out the lone pair would be in. But in any case, you can see from a side view that this pi star is at least pointed out directly towards the lone pair. Now, it's kind of skiwampus, right? We're not, is that a word? That's a word, yeah. It's not, I mean, it's sort of the backwards Bürgi-Dunitz angle. Ideally, you'd want it to approach from there. But the point is that rather than being sort of constrained, no matter how you rotate around these carbon-carbon bonds, you're never going to get that lone pair oriented towards the pi star. Here it's just hanging out in the exact right plane. And probably you're able to, anyway, so at least part of this has to be related to the ability of orbitals to reach each other. Saw a hand. Logan, was that you? No? Okay.
I was going to ask you what angle it was, and then you showed.
Yeah, I don't know. We could probably calculate it. That looks like, it's not 90 degrees, it's not 30, so we'll call it 60. Yeah.
Okay, I don't know why I'm still stuck on this. But on, like, why doesn't the alkene one form? Like, the one that doesn't work.
Yeah.
Why doesn't that one form an enol?
It should have done. I just left it like this to make, because the issue is, remember when we're deciding whether it's endo or exo, the issue is, does the atom that have the negative, gets the negative charge, is that inside the ring versus not? We could have easily drawn the resonance structure for that in this enolate form. Sorry, getting ahead of myself. We could easily have drawn it in this enolate form. Then we could have drawn it forming, there was an oxygen there. Oh, this is terrible. Forming the enol and then tautomerizing to the ketone. I don't actually know. I haven't read this paper, so I don't know whether they are able to detect any enol formation. My guess is no, because again, the enol for that one is going to look like this, which seems too horrible to comprehend. I mean, yeah. Yeah.
That makes sense. Thank you.
Okay, yep. Another way of saying that is, as drawn, I mean, if we were to think of this, if I were just to draw you this and you didn't know anything about forming enols versus ketotautomers, if I were to ask this in an introductory OChem class, you would tell me that this lone pair is in an sp2 orbital orthogonal to the pi system. So it's not actually conjugated to the carbonyl oxygen, at least as we've drawn it. Okay, so the bottom line is Baldwin's rules have to do with, especially with this area where it's most important, the 3, 4, and 5 membered rings and sp versus sp2 hybridization. Is geometry such that the nucleophile can access the empty orbital, the pi star? Can you get an angle that's reasonable? And that appears to be the sort of basis for these rules. Okay, so anyway, so yeah, and maybe now you can aspire to be the jerk that sits in the audience and says, well, that's actually a 5 endo-trig cyclization, and anyone knows that those are disfavored according to, what were the rules again? Do you remember what they were called, right?
I feel like this has happened to you.
No, it actually hasn't, but yeah. I mean, occasionally when you go to grad school and you sit in seminars, especially at places where people have decently high opinions of themselves, you will get, there's always the one student that has something to prove, that wants to ask a question to impress other people. And then occasionally you'll get faculty members going at each other while talking to the speaker. There was one guy that would show up to seminars at Wisconsin. The students would do a third year seminar. Instead of, it's kind of like here we do the literature talk in the, I don't know, any of you that are grad students, maybe Sam, you've been here, and Nate, you've been to the 692R class where you give a talk on a literature presentation. At Wisconsin, the requirement was you gave a 45-minute talk on an area of literature, not just a paper. But this one guy, one professor, would bring his own laser pointer to the talk, and he'd, highlight some things on your slide and ask you to explain stuff, and yeah.
Wait, who?
Oh, he's not there anymore.
He's not.
Yeah.
He's just like avoiding this man.
May he rest
It's
in
like-
peace. Yeah.
Never mind.
I don't think he's living anymore, so may he rest in peace. And there was another guy that during one talk, he was responsible for actual famous sort of transition state discussion that describes, I think, aldol selectivity, but he was trying to take credit for the Felkin on model, even though he was neither Felkin nor on, and it was kind of weird. So you can see some fun things in grad school. I'm just trying to prepare you for this. You will all have vulnerabilities, but now I give to you the armor that will protect you from the annoying Baldwin's rules question, all right? Okay, where were we? Radicals is the next topic. There's a lot we could say here, but maybe don't need to. Maybe I'll just start by, what doesn't make sense to you about radical reactions?
When they're acceptable versus when they're not.
Okay. What do you mean when they're acceptable?
Like, I guess, it's probably like in terms of like homolytic versus heterolytic, but like why? Like, I feel like there are very specific situations when you're like, this forms a radical versus this, the electrons just push.
Okay. When are radicals reasonable intermediates? Good, that's a good question. Yeah, what else?
The question of like regioselectivity on like the propagation or
Okay.
propagation stuff, kind of like why it would go to like a terminal carbon or like an internal one.
Okay. When are radicals okay? And what about the regioselectivity issues? Okay. Others? Yeah.
Just kind of interested in like how strong the light has to be, or how
Okay.
weak the bond has to be in order to like do the homolytical cleavage of.
Okay. Practical issues. I'm not going to be any help whatsoever there because I've never done a radical reaction. But I can tell you some things about bonds that are weak enough to generate radicals. Radicals, of course, are species with unpaired electrons. Okay? And we can talk about their reactivity. It turns out because they're not fully positively or negatively charged, the electronic issues that we use to think about carbocation stability don't matter quite as much as we deal with regioselectivity issues. But radical reactions usually need an initiator because unless you have a molecule that's just has an unpaired electron, and there are some that are stable, you need something to split up a pair of electrons. You need something to break a bond. So that's the concept of radical initiators. And how you do this is dependent on a lot of factors. You can do it with light and heat, or heat. You basically need a weak bond that you can break with either light. This is how organic chemists write light. that's the energy of a photon, but that's what we've adopted. Or heat, this is how we write heat, the little triangle, the Greek letter delta, which looks like it's on fire. Nobody ever draws the fire. So examples of, so a weak bond that you can break, and you want to break it homolytically, that is, each partner gets an electron. And that's why you're going to notice that the radical initiators that I'm going to draw, in general, at least the first few, are going to have weak bonds that are between the same kind of atom. So a classic weak bond is an oxygen-oxygen bond. So here is T-butyl hydroperoxide, or no, just T-butyl peroxide. At 130 Celsius, so, okay, maybe not every molecule you're dealing with can tolerate that high temperature. That's enough thermal energy for the bond to undergo homolytic cleaving. How does that happen? What's going on there? I assume it's just that you have enough kinetic energy in the system that you take the spring constant for that oxygen-oxygen bond and you stretch it to the point that they just fly apart from each other and each one gets an electron. That's more favorable than one of them getting 2 electrons and the other getting a positive charge, because oxygen's electronegative, right? So this is an amicable divorce 50-50 split of assets. Due to irreconcilable differences. Okay, and let's see. They've done a little bit of kinetic studies on this. The entropies of activation in a lot of cases are positive. Entropy units, that's I think calories per mole per Kelvin. But that's because you're splitting something up into 2 things. So that's part of the thermodynamic driving force. So that's T-butyl peroxide. Another radical initiator is aza-isobutyryl nitrile, or AIBN. You heard of that before? Yeah, probably not drawing it right. This you can initiate at a much lower temperature. And this has got a couple of things going for it. Now we're not talking about necessarily a weak oxygen-oxygen bond, but we're talking about a molecule that is spring-loaded with something that wants to escape as nitrogen, right? So if we break the carbon-nitrogen bond in a homolytic fashion, we make nitrogen gas. I don't know that that arrow accurately conveyed what's going on. Making a new bond there. And that's irreversible, right? Because it's off into the atmosphere. And then you have 2 of these radicals, I don't know, alpha cyano radicals. It turns out that we'll see that both electron withdrawing groups and electron donating groups can accelerate radical reactions. You can stabilize the radical either by electron donation or by electron withdrawal. That seems a little bit weird because you can't stabilize a negative charge by electron donation, but this is not a negative charge, this is just a single electron. You may be used to thinking about radicals as electron deficient species, but they're more electron rich than carbocations. And so that's one thing I had to learn that's different between radicals and carbocations versus carbanions. Radicals can be stabilized by both electron withdrawing groups and electron donating groups. So this is this iso. Did I do something wrong there? That's the right number of carbons, isn't it? Yeah. Close enough, apparently. Oh, okay, I get it. The fourth carbon. Anyway, this is AIBN. I'm trying to figure out where the butyryl came from because there's only 3 carbons, but no, actually it's the one there. So, okay, whatever. Sorry. So you get 2 of those radicals, and they can be initiating. Let's see. There are other examples, but I think that's good enough for now. Again, the activation entropy is favorable, 12.2 entropy units, and you'd think so because you're making a gas that bubbles off. In general, you want activation enthalpies for these reactions are in the range of plus 30 to 40 kilocalories per mole, which is close to the bond dissociation enthalpy for the bonds that are being broken. So the reaction is slow because of what you would expect. You have to break a bond and you have to pay for it. But the transition state involves a high degree of radical character, and so you've got to pay for breaking that bond before the reaction can proceed. You pay for it to some extent, though, by breaking a couple of things apart. So that's radical initiation. Now, there are, once 2 radicals form, you've got options, because remember that 2 radicals form in a solvent cage. There's solvent molecules around. So we're going to illustrate that with, not that this happens in water, but because it doesn't, but there is our solvent cage. Ooh. So you've got sort of 2 options that can happen. You've got escape, in which one of them gets free and can now go on to do other things. He's sort of winking. Or you have recombination and or sometimes called internal return, whereby the 2 radicals just meet up and form the new bond again, and you go back to starting material. And things that can promote versus inhibit escape. If the solvent is viscous, I guess, I don't know, that will slow escape. Viscosity refers to how sort of tightly the molecules in the solvent are holding on to each other, and if they're holding on to each other more tightly, it's tougher to get them out of the way so that you can escape. All right? Okay, another, well, I guess we're about done. So there's another method of radical transfer that involves a radical formation that involves single electron transfer and fragmentation. Your text has some stuff on that. I know basically nothing about it, so I think we're going to skip that. All right, so we still need to answer the question of, we've talked about when are radicals okay. I mean, they're okay when you use an initiator to form them. I think in the Castle lab with the amino radical thing, the molecule you're dealing with, you pre-synthesize, it's self-initiated, right? You have a weak oxime NO bond that you, I don't think you guys use light. I think you just stick it in the microwave, add heat, and then you just get homolytic cleaving, and you're left with a radical which cyclizes on itself, because at the right position, there's 5 atoms away, there's a double bond that can be attacked. Anyway, so we'll have a bit more to say about radicals and regioselectivity. The text doesn't spend a lot of time. There's whole textbooks on radical chemistry, but we'll spend just a little bit of time on that. We'll talk about carbines, and then we'll get to elimination reactions. And you know, maybe someday we'll get to chapter 11. If we don't, you will have been cheated, but you have your text, so go teach yourself.